came from Berkeley. Sometimes they're distracting and I'll take them out. Other times they kind of say some concept.
Yeah, that's
yeah, this, I mean, the Berkeley curriculum is amazing. Immersive. And I deviate from that.
You come out on Sundays.
Oh, it's time. It's finally time. Can you guys hear me in the back? You guys excited in the back? That's why you sit in the back, right? You guys excited in the front? Yeah. I'm excited. All right. Let's get started. Constraint satisfaction problems 2. Twice as good. Twice as exciting. Okay. Let's start with some announcements. We finally, I hope, fingers crossed, resolved the TA office hour issue. So if you ever found yourself in office hours and you felt like you were in the wrong place, but we told you it was the right place, or there was a class going on that you weren't particularly interested in attending and that was in your office hours, hopefully we fixed it. So I would point your attention to the red text here, which is the part that has changed, and I've updated the syllabus to reflect this. Okay, TAs, please let me know if there's more problems. The issue stems from the fact that we have a new category of classes now, data science classes, that weren't sharing the same calendar in some way that I don't understand. So hopefully we fix it. Okay, go to office hours, learn lots of things. All right. I added this a second ago, that's why it's in my handwriting. Project 1 is coming soon. It has come to my attention that you can see Project 1 right now in the files section of Canvas. That is an unofficial Project 1 version, and it's probably exactly what we're going to assign you, but we're still waiting for the final thing. So sorry about that. There will be an announcement either in class or over Canvas when that gets assigned, and we'll go from there. Sound good? Okay. Quiz 2 will be up after class today. It covers CSPs. It is due tomorrow right before midnight. It is, I think, easier than Quiz 1 was. Kind of an attempt to, if you've been paying attention in CSPs or you've been reading your book, to kind of get some points. So that's Quiz 2. Don't forget to do it. Homework 1 is live. It should be live as of a few minutes ago. Can somebody who's looking at cat videos tell me if you can see homework 1? We're good. Okay, cool. In fact, let's look at it together. Homework 1. Okay, it has 2 problems. One about graph search, the other about graph search. Just an abstracted version. Okay, so similar to the exercise we did in class, read through the instructions very carefully, but the rundown is, here's a graph, it has edge weights, it has heuristics. You're going to enumerate graph search of a variety of types on this, okay? The second one is like a word problem that can be structured as a graph search in order to be solved. So you will do so. Well, there's some questions about kind of how you structure it and what that structure implies and things like this. So I want to point out one thing, and that is that this question here says dimensionality of the state space. It does not say cardinality. So this should be an integer value, it should be relatively small. Sound good? Okay, so take a look at homework 1. It is due Tuesday, right before midnight. Okay? It should, I mean, it will take you a little while to work through the problems, but it's not going to be conceptually very difficult, I hope. Okay? Awesome. And then project 1 is coming hopefully maybe today or tomorrow, and we'll go from there. Okay. Clarifications from last time. I don't think we require any clarifications from last time. Do we have question?
Online, homework due the 30th.
Does it say the 30th? And I just said the 28th? Well, I guess that means it's due the 30th.
Well, I think it says available until, which
it's available until the 30th,
latest.
but the due date's the 28th.
Oh.
Does that make sense?
So you can view the files until the 30th, in case you're taking advantage of our 2 late days. Okay. All right. Forget what I just said. It's due the 28th. Good? Okay, cool. Any clarifications from last time? Questions about CSPs from last time? Yes?
You're probably just reviewing
So do you do minimum remaining values the same time as least and training values, or are those two different choices that you're making?
So they are two kind of distinct choices. One guides your ordering of variable assignment, and the other guides, once you have a variable to be assigned, the assignment of the value from the domain. You should use both, most likely, if you can. But they're kind of hitting two different steps in that. Does that make sense?
Yeah.
Yes.
There were two terms, I'm not sure how they relate to each other, but filtering and forward checking. Is forward checking a type of filtering, or how
Yes.
does that?
Yeah, so filtering is a concept of restricting domains. You're kind of filtering the available domains, right? Forward checking is an instance of a filtering algorithm.
Could you go over what forward checking is specifically?
So forward checking is when you assign a value, you enforce that the edges outgoing from that assignment are consistent. So you restrict the domains of the children of that variable that you just assigned in the constraint graph. Cool. Any other clarifications from last time? We'll do a little bit of review today too. Okay. Clarification from 2 times ago. So I kind of punted last time and said I would get to these. I'm now getting to these. So there were kind of 2 questions that I wanted to cover. One is, what kind of bookkeeping, extra bookkeeping do you have to do in graph search when you're talking about BFS and UCS? We talked about kind of restrictions on your heuristic value for A star required with making the graph search version work, right? But how does that extend to BFS and UCS? Okay, so to remind you, the difference you do is you keep around a set of expanded nodes in the version I described, right? And every time you expand a node from your priority queue, you only add its children if you have never seen it before, right? And if you've never seen it before, you add its children and you add it to the expanded set, right? So that's kind of that's what makes graph search not tree search, right? Okay. So what extra bookkeeping do we have to do if we're doing the graph search version of BFS and UCS? So the answer is, if we do our check when we're dequeuing, the priority queue will kind of handle it. So we're not messing with optimality of BFS or UCS. Does anybody see, it's really easy to see why that's the case for BFS. Can anybody point that out for me? So in BFS, your cost is the depth, right? And you are exploring by the properties of BFS, popping things out of the queue in their order of depth, right? So without any extra bookkeeping, if you pop something off, you will have already popped off a goal previously if one exists, right? Okay, and then for UCS, you can see that you don't need to do extra bookkeeping with a similar proof to what you would do for A star. In fact, you could use A star's proof exactly to show that, and that's because the null heuristic 0 is consistent. Okay, so let you guys think about that for a little bit. We can talk about it more later if you'd like. Does that sound good? All right. We also had a question whether you would want to check your visited set prior to enqueuing or when you're dequeuing states. And the answer is you can do either, but it's going to require extra bookkeeping if you do it before, because you're going to have to check your frontier or your fringe as well. Sound good? Okay. There was also a question, I think it was on YouTube, a comment posted, is that right? That the heuristic values and the costs for the examples I worked ad nauseum on the board that one day were not visible in the video. Here they are. They are now part of the official record. Go forth and watch videos. Okay. Also, it makes me nervous that there's commenting allowed on this video.
Could disable it.
We'll think about it. All right, quiz 1. I want to touch on this. The average grade for quiz 1 was an 82%. That seems a little low to me. Quiz 1 was very similar to a lot of things that I covered in the lectures exactly. And so let's go look at it and we'll see if we can either just get a review or identify maybe some of the problems with the quiz. Okay, does that sound good? All right. No. If I have to log in. do some quiz one next time. Yes.
I was just gonna ask, can you see what question most people missed?
Yes, I can look at the statistics. So one of the biggest problems was in the state space question. The two most popular answers, okay, so we were doing pathing, right? Let's see if I can remember this exactly. We were doing pathing for Pac-Man, which exists on a 2D grid, right? There were 4 ghosts, maybe. There were 30 food locations, right? And the question was, if we want to do pathing, going from one point on the board to another point on the board, what's the correct choice for the state space representation? And it was a 10 by 10 board, is that right? 10 by 10 board, yes.
Was that the one that was asking specifically like the least amount of state space that you could store?
Yes, yes. Okay, so the most popular answers were 100 and 400. So the correct answer is 100, that's what I was looking for. Can anybody tell me what's wrong with 400? Yes.
You don't need the direction that Pac-Man is facing,
Why don't you need the direction that Pac-Man is facing?
because you can move in any direction no matter where he's facing.
Because in this instantiation of Pac-Man, the direction Pac-Man is facing is functionally a graphics concern, right? It's kind of sugar on top of the stick at the game. You can transition from any orientation in all 4 directions, regardless of the direction that Pac-Man is facing, right? And there's no restriction on the goal state associated with Pac-Man's orientation, right? So in order to get from the start to the goal, you only need the position on the board being 100 rather than 400. Does that make sense? Yes?
When I went to look at the slides, just to be sure before I answered, the 400 or whatever type of answer was the only information I could find on the slides about it.
Okay, I'll look into that. If that's the case, everybody gets a free point on the quiz, right?
Yeah.
They get this problem free.
It included the directions in the state.
Okay, I'll do that. If that's the case, then I was ambiguous and I apologize for that. Okay. All right. Any other questions that people had a particularly difficult time with on the quiz? Or we can look at all the questions next time. All right. Let's move on then. Okay, last time we covered CSPs. Very exciting. We looked at backtracking search. That is a search algorithm for CSPs that is built on what search algorithm we've learned so far? DFS. Exactly. That might be important information for your quiz. Okay. We talked about constraint propagation, right, in a various number of ways. This is filtering. We talked about forward propagation. We went over that a minute ago. That's where you assign a value and you look at the edges associated with the node you just assigned, and you restrict the domain of the children, right? We also talked about arc consistency, right? This is where you ensure that all arcs are consistent by our definition of consistent at any given part of the algorithm, right? Usually after an assignment is made. We talked about ordering. These are other ways to speed this up. You can do minimum remaining values. That's when you decide what node to assign next in your search, and you pick the one that has the least possible choices left to it. And the intuition for why we do that is we want to fail fast, early, right? We don't want to make a choice that has negative implications down the road and not know it for a long, long time, right? Okay. We also talked about the least constraining value. This is when you're choosing from your domain, once you've already decided what node you're going to assign a value to, which value in the domain to assign, right? And this, you want to do the one that imposes the least number of constraints, right? And the reasoning there is you don't always have to assign every single possible combination of values, so let's try to get an easy one, right? Okay. Today we're going to talk about exploiting structure. I promised we would do that last time, and so we will. And so that's going to make these more efficient even. We're also going to talk, if we have time, about local search. Okay, so a reminder on CSPs, we have variables. Each variable has a domain, which is a set of values that they can take a value from. And there's some set of constraints. These can be implicit, as in they're described conceptually or by code that has to be executed in order to determine whether the constraint's satisfied or not. Or it can be explicit, and that's where you provide exactly a list of legal tuple values, right? Okay, we can have constraints that are unary. That's functionally a restriction on the domain of one of your variables. You can have binary constraints. That's what we spent most of the time talking. That's a relationship between two of the variables, right? You can extend that up to higher orders to n-ary constraints. We will talk a little bit about that today, maybe tangentially, but we're not really going to get into it too much in this class. Okay. So the goals here are to find any solution. That's kind of what we're talking about in this class, right? But there are also variations where you want to find all of the solutions that satisfy the constraints. You want to find the best solution under some cost metric or some fitness value, right? Okay. So the main algorithm that we built everything else on was backtracking search. Quick reminder, this is recursively described here, but basically the highlight is that if you get an assignment and it is fully complete, by the construction of the assignment, it satisfies the constraints, right? So you know, that's great. Otherwise, we have these two choice points where we're choosing which variable to assign a value to at any given step, and we're also choosing which value from its current existing domain to assign it, right? Okay, we talked about improving backtracking, right, with all these ways we've talked about so far. The idea here is that these can, in practice, give us huge speed ups, but at the end of the day, the problem is still NP hard. So there are going to exist worst cases where you have to enumerate all possible combinations of assignments, right? So filtering, the concept here is to detect inevitable failure early, and that's by propagating the implications of any given choice as far as you can, right? Okay. And then we talked about the ordering, and today we're going to talk about structure.
Is our consistency an example of filtering?
Arc consistency is a property. Enforcing arc consistency is an example of filtering. Okay, as a reminder, we have an arc, right? This is a directed conceptual edge that's going from one state variable to another, right? And when we delete things, we take them from the tail or the trunk, as illustrated by this, right? Okay, that's important. Let's go through this very brief example again. So, if we look at this arc from V to NSW, is this consistent? So to remind you, what we do is we enumerate all of the assignments for the tail, that's V, right? And we say, for every one of these, for each of these, is there any assignment at the head that works according to the constraint, right? So if we assign conceptually value V red, then NSW could be blue. If we assign it green, NSW could be whatever of the two remaining choices. And if we assign it blue, then NSW could be red. So this arc is consistent, right? Okay. Similarly, if we look at the arc from SA to NSW, is this consistent? All right, so this is really important, right? For every value in the tail, that's blue, there is any value in the head that works, right? There just must be one. So this is consistent. Okay, what about going the other direction? Is this consistent? Why is it not consistent? If you choose blue, then you're host, right? Okay, so what do we do to enforce consistency then? Yeah, we're gonna delete it, right? Let's see if this works today. You ready? Hey! Round of applause for the Apple Pencil. Awesome. And for me, for remembering to charge it this time, which I think is half the battle. Okay, so now we've made this consistent. We deleted from the tail. That's important. Okay. But remember, we had this problem where we had previously checked this arc and it had been consistent. We did a check and enforcement of arc consistency on a completely different arc, and now we have to return to this, right? Because we've changed it. And does anybody remember heads or tails, which the thing that changes triggers this kind of behavior? If you change the values in the head, you have to check all the incoming arcs. Okay. And so is this arc still consistent? It was consistent last time. Is it still consistent? No. And why not?
Choosing red.
Right. Remember, for every value in the domain at the tail, there must be a value, any value in the head that works. Every value in the tail of V includes red. There is no value in the head that would work for that assignment, so we have to get rid of this. And then we'd have to check all the arcs going into V, right? Yes.
Does what we end up deleting at the end depend on which arcs we check first, or will it always kind of resolve itself in either an impossible situation, or like the same impossible situation, or the same valid arc consistent state?
That's a really interesting question. My intuition says it'll result in the same, regardless of the ordering of the arc checking. but I'm gonna double check, and we'll have a whole section on it next time. That sound good?
Yeah.
Okay. Awesome. Okay, so now we arrive in this checking here, this enforcement of our consistency, at the real crux of the problem, right? We as humans who are smarter than this algorithm saw this problem coming. Now we're going to identify it over the course of the algorithm. Is this arc consistent? No, it is not. So we would delete this. We notice this is an empty domain. We stop, right? And backtrack. Yes.
So whenever we delete a color during the arc checking process, do we actually start? Do we have to start the arc checking process all the way back to the very beginning, or is it like?
In the worst case, it will affect every arc.
Oh, okay, every arc.
down the road.
Oh, okay.
These are hard problems. There's no free lunch. Okay. 99% sure. I'll double check. We'll talk about it. Okay. So our consistency detects failure potentially earlier than forward checking, because forward checking is a subset of enforcing our consistency, right? This is important. If x loses a value, the neighbors of x need to be rechecked, and on, so on, and so on, and so on. And we have to rerun this after every assignment. This is some subroutine in our larger algorithm, right? And so this is sitting inside of backtracking search. Okay. After enforcing arc consistency is important. A variety of things can have happened. There could be one solution left. There could be multiple solutions left. There could be no solutions left. We may or may not know that there are no solutions left. Right? And again, super important, our consistency still runs inside backtracking search. It isn't its own search. And what happened here? Would our consistency identify this issue? No, it will not, right? Because conceptually this is an issue with 3 nodes. As soon as you assign one value to one of these 3 things, our consistency will determine this problem, but it's not smart enough to know this just by looking at it, right? Okay, so let's generalize this concept of consistency to higher orders. And so we're going to talk about something called K-consistency. So kind of our base case is one consistency. This is sometimes called node consistency. And that's where every single node's domain has a value which meets that node's unary constraints. This isn't really an issue. You can go at the beginning of your search and just enforce all your unary constraints, make sure your domain's not empty, and continue from there, right? But formally, this is one consistency. 2 consistency is arc consistency. This is what we've been talking about this whole time. And that's for every pair of nodes. Any consistent assignment to one can be extended to the other. Any pair of nodes. Right? So this is a property on the constraint graph. Any pair of nodes. All right. Then there's higher orders, K consistency. So for each K nodes, any consistent assignments to K minus 1 of those can be extended to the Kth node. So there is a consistent assignment to the Kth node, given that you have a consistent assignment to the K minus 1. Right? Okay. Higher K is more expensive to compute. In practice, I think people generally may stop at 3 consistency most times, but this is a mathematical concept that goes up. All right. Slightly differently, there is a notion called strong K consistency. And this just means that if you have K consistency, you also have K minus 1, K minus 2, all the way down to consistency. Awesome. Okay. So I'm going to claim this is the case. If you have strong N consistency, where N is the number of nodes in your graph, it means you can solve that without backtracking. All right, so this is relatively intuitive, but basically the idea is you can choose any assignment to any variable from this domain. You can choose another variable. You were able to do that assignment because it's one consistent, right? Choose a second variable. By 2 consistency, there's a choice there, consistent with the first. Choose another one. You can just keep grabbing these, going through, and get all the way to the end. All right, why is this not generally useful? Can anybody provide some intuition? Yes?
Would you have to like run the CSP algorithm to figure that out?
It's basically just as expensive as solving the problem in the first place. But there's a big spectrum here. There's a lot of middle ground. So it can be worth doing 3 consistency, 4 consistency, depending on your problem. 3 consistency is a special case called path consistency, and that actually happens in practice pretty frequently. Okay. So let's use a little bit of this concept to talk about exploiting specific kinds of graph structure in order to solve CSPs, specific versions of CSPs, much more quickly than we would have otherwise. Okay, so here's our constraint graph for our coloring of Australia that we've been talking about all week. And what we want to leverage here is an extreme case of problem substructure called independent subproblems. So does anybody remember the property of this graph that makes this have multiple independent subproblems? Yes?
It has 2 strongly connected components.
It has 2 connected components. Disconnected components in your constraint graph imply independent subproblems, right? Does everybody see why that would be the case? You can choose any value here, right? And it's going to have no effect on the solutions of this graph. Similarly, any valid assignment up here is going to have no implications for Tasmania, right? Now this is true if Tasmania isn't just a single node. If it's its own separate connected component, this also, right? Okay. Independent subproblems are identifiable as disconnected components of the constraint graph, right? So each independent subproblem is its own connected component, right? And we learned how to identify connected components in our algorithms class. Is that correct? Good. This is my first semester here, so the specific curriculum here I'm still learning, right? Okay, good. Okay, is this useful, computationally speaking? So suppose you have a graph of n variables, and you can break this up into subproblems of only c variables. Let's look at the complexity. So the worst case solution cost is going to be n over c times d to the c. That's much better than the worst case cost of the whole graph, which is d to the n, depending on your c. Right, can anybody tell me why it's n over c, d to the c? It's not a trick question, it's pretty simple. Yes?
So n over c is the number of subproblems, and then d to the c is the cost of each subproblem.
Exactly, right. And so to get some intuition to how big of a difference this can make, let's suppose you have a problem that has 80 nodes. That's not very big, right? D here is 2. Each value can take on 1 of 2 values, 0 or 1, for instance. And we can break this up into 4 problems of 20 variables each, right? If we don't break this up, and in the worst case we have to enumerate all the possible solutions, which will sometimes happen, this will take us 4 billion years to do if we're processing 10 million nodes per second. That's a long time. If we break it up into 4 equally sized subproblems, we're going to get this done in 0.4 seconds. It's different, right? So this matters a lot, right? This is extremely powerful. 4 subproblems is not that many subproblems. Right? We didn't have to break this up into a bunch of tiny little pieces. It's just 4s, right? Okay. In practice, this may not actually come up that often because generally people are pretty good at identifying their independent subproblems before you even start searching. But if you are not positive you don't have independent subproblems, you should run connected components and make sure that you don't. Okay? Awesome. All right, something that comes up a little more often. CSPs that are structured like trees or almost like trees. Okay. So I'm going to make another claim. If we have a constraint graph that has no cycles, we can solve this CSP in order n times d squared time. Linear in n. What that can be. Right? That would be awesome, right? That's much better than d to the n, right? Linear compared to exponential. Okay. This property also applies to probabilistic reasoning, which we'll see later on in the semester. All right, so let's look at this, or why this might actually be the case. So what we're going to do is we're going to talk about an algorithm for solving a tree-structured CSP. Yes?
Something just occurred to me, sorry. Perhaps if the constraints are one way, then you can like topologically sort a graph and make a tree out of it and then solve it there.
Yes, that's what we're about to do.
Oh.
Okay. Well, we're going to topologically sort this tree. But directed constraints in a constraint graph don't really make much sense. Because you're just describing participation in the constraints by your variables, right? I don't want to say there aren't constraints that are directed, but I can't think of one.
Yeah, I guess thinking about it, it's a little bit of a weird one. Like, it's like they should inform each other, right? For it to be a constraint on each other.
Right.
But otherwise, I guess it would be unary anyway.
Maybe. I can't think of an easy example of a directed constraint. Anyway, okay, so let's look at this undirected tree, right? So what we're going to do is we're going to choose some variable as our root. In an undirected tree, any node can be the root and it's still a tree, right? Okay, so pick one. Shake it upside down. Topologically sorted. Right? Okay, so now these are directed. So very good intuition. What we're going to do is we're going to work from the right to the left, enforcing our consistency. Okay? So let's say that each of these variables has some domain shown there by their specific colors, and these are restricted maybe by unary constraints or by some other consideration that we'll talk about in a little bit. Let's say this is the domain. These are the domains for each of the variables or maybe two, right? Okay. So what we're going to do is we're going to start at the right. We're going to take our arcs that are directed according to these arrows, these directed edges. We're going to enforce arc consistency from the right to the left. Okay? Removing values from the trunk, right? Okay, so let's look at the arc from D to F. Is this arc consistent? Why is it not? Blue doesn't work, right? Okay, so let's get rid of blue. All right, so we start at the right, right? We're looking at F first. All the arcs coming into F. There's only one arc coming into F. Why? Because it's a tree, right? Okay, so we made that arc consistent. So now we're going to move this way in our ordering. We're going to look at E. What is the arc coming into E? D to E, right? Is that consistent? So a mixed review. Who says yes? Who says no? It is consistent. So let's remember that for every value in the tail, which is D, there is a value in the head, which is E, that works, right? So to go through it again, if we pick red at D, either of the values in E would work, but we only need one to work. And if we pick green at D, blue would work at the head, right? So it's consistent. Okay, moving on. Let's look at D. So what's the arc coming into D? Is this consistent?
Yes.
Yes? Okay. And C, B to C, is that consistent? Nope. What do we need to do? Get rid of green. And then coming from A to B, what do we need to do? Right? Okay, so we went from right to left, we enforced our consistency all the way. So now what we're going to do is we're going to go left to right. We're going to start assigning values. Okay, so let's start at A. What should we pick? That's probably pretty easy, right? All right, so A is red. Now we move on to B. We assign a value that's consistent with the choice of its parent. So this we actually have to look at, right? So we can pick B. Why will there be a choice that's consistent with the parent? That's what we just did, right? Okay, so there is one, so we just need to figure out which one it is at least, right? Okay, so in that case, screen here. We move on to C. What do we choose at C? Not much choice. It's going to work with B's assignment. We made sure that's the case. Okay, now we have one that we can choose from. So we have D. Red's not very interesting, but let's say we pick green. Does everybody see why red's going to be less interesting? Okay. Either works, right? So we pick D. We pick green. Okay, so now we move on to E. and now we actually have to care, right? So green's not going to work at E. But there is one, we ensured that already. We pick that one, we move on with our lives, we make an assignment. We solve the problem, right? Okay. The runtime here is order n d squared. Can anybody say why it's order n? Yes?
For our consistency check, you have to go through all the numbers.
You had to go through all of them in one way, you had to go through all of them in the other way, but that's just 2n order, right? Exactly. Okay, and why d squared? Yes?
I was wondering what D was.
So d is the size of the domain. Let's say it's the size of the largest domain here. It's d squared because you kind of have to check each pair of adjacent constraints against each other as you do the assignments. Anyway, that's a lot better than d to the n, right? Yes?
Why was it in this example that like C only has green available to it while B has green and blue available to it?
Yeah, so
Arbitrarily chosen or?
well, it's chosen kind of for exposition in this example to make interesting things happen. But it could be the case that there are unary constraints on C, right? C must be green for some reason that we haven't described, but it's part of the problem structure. Or there could be another case, which I'll get to here in a minute, that would cause you to have a restricted domain on a tree problem that is coming from a not tree problem. Okay. So we kind of went over this a little bit, but after the backward pass, all root to leaf arcs are consistent. That's what we enforced, right? So why is this the case? Intuitively, we're going from right to left. You only have to recheck things if you've modified the head, right? But we're modifying the head and then the tails. That's the ordering we've done, right? So we don't have to recheck. Make sense? Okay. Then, if all the root to leaf arcs are consistent, forward assignment will not backtrack. We talked about why that's intuitively the case already. There is an easy proof. You can do it by induction. I'm not going to do it, but you can do it. Okay. Why wouldn't this algorithm work with cycles in the constraint graph?
You can't talk a lot before the cycle.
Right. We had more edges coming into F, right? Let's say we had this edge here, right? C to F. So we make all of these consistent, right? So the arc from C to F will be consistent. The arc from D to F will be consistent by the construction. But we can't guarantee they're consistent simultaneously, right? That the assignment for one won't break the assignment. Okay.
Is that a cycle?
It is a cycle in the constraint graph, which is under it.
Oh, yeah.
Okay. This concept is going to come up again when we talk about base nets later in the semester. Spoiler alert. All right. What are some other ways we can improve structure or leverage this concept in constraint graphs that aren't trees to begin with? What about things that are almost trees? So let's define something, a process called conditioning. And conditioning is where we instantiate a variable and prune its neighbor's domains based on that instantiation. Okay. Now that we have this concept, what we can do is take something that's almost a tree, instantiate a part of it, restrict the domain of the remaining values, and have a tree in the remaining to be assigned variables. Right? This is a process called Cutset Conditioning. And the idea is that we're going to instantiate in every possible way a set of variables such that the remaining constraint graph, when we cut them out of the graph, is a tree. Right? So you can see that if we set SA here to red or some value, we can prune red out of the adjacent nodes, domains, right? Pretend it doesn't exist anymore, and we're left with a tree. Then we can solve that tree, right? We just learned how to do that much easier. Cool. So why don't we do this, right? Why don't we just do this every time? Yes?
Hey,
So let's say that there's some subset of nodes. That's correct. In that case, you wouldn't have been able to make this a tree by Cutset Conditioning SA. But there might be some subset of nodes that you could cut, right? To turn this into a tree? Yes.
So if we were to pick like SA and say we pick some other like NSW to remove from this, and could you prune another tree that way? Like,
Oh yeah, there's multiple ways to cut this graph so that it's a tree left, right? Like you could cut NTQ and NSW, right? You're left with a tree and the remaining variables. And you could do this, right? You would just have to enumerate all the ways that you assign NTQ and NSW, right? And you have to do your tree search multiple times. Your tree assignments multiple times. Yes?
As you prune more nodes, the amount of ways that you have to check those grows exponentially.
Yeah. So you have to check every possible assignment of the cut set, the set you cut, right? And that's going to be exponential in that number. But if that number is small, it's definitely worth doing. Yes?
in case such as this, where like our first color selection of SA is sort of arbitrary, like could be red, blue, or green maybe, would you even want to like say you pick red for SA, could you just go with that pick and find the same solution you would if you started with blue or green? Because
So if you
color
pick,
selection's arbitrary?
if you pick red, then that's the results of that are going to propagate off of the graph. So it's not going to be the same solution as if you had solved it with SA as red and then solved it with SA as blue. Those are going to be different. And in fact, there may only be one solution associated with one of those assignments that you don't know in advance. Yeah.
Is it like if you have a general problem, it's hard to tell if it will be cheaper to treat them?
Yeah, so what you want to do is you want to find the minimum subgraph that if you cut it, you have a tree left, right? That problem is NP hard itself. So there's no free lunch, right? But if you have some reason to already know or identify a small cut set that makes your graph a tree, this works really, really well. And that's sometimes the case, yes?
So does that involve the possibility to figure out a nearly structured conditioning graph and then get into a tree? Does that involve like cycle detection and stuff like that? Or what are you going to approach?
Yeah, so to know, okay, so I don't know the best algorithm for finding the minimum cut set off the top of my head. There are ones out there. But you have to at least implicitly detect algorithms because, or cycles because you have to know you're left with a tree, which by definition, and in fact that's the definition of a tree, right? Yeah, so you get this trade-off between an exponential growth in the size of your cut set and the cost of solving the tree compared to the cost of solving the whole graph, right? It's just hard to identify that cut set in the general case. Yes.
So for instance, in our last example where we already had a tree, but then you added a cycle into it, we could cut the two of them that already had Euler constraints on them and make it into a good tree again.
So definitely there's some relationship with the size of the remaining domain and what you would want to cut, which I think is what you're getting at. Yes, with that previous graph, we could have cut one of the nodes involved in the cycle and had a good tree left. If you cut ones that have unary constraints such that it restricted the domain, you're going to lower this constant of how many times you're going to have to do this problem right, because if you only have to enumerate that value twice instead of 3 times, you've saved one of your tree searches, right? But generally speaking, that tree search is so much cheaper than doing the whole graph that any way to make it a tree search instead of the graph with small cut set size could be worth it. Okay. Sometimes you can make this work. If you can, you definitely should. But since we're working on NP-hard problems, there's no free lunch. So, that's the takeaway. Yeah. Okay. So the cut set size C gives us a runtime. I should have said this earlier probably. D to the C. Why D to the C?
You have to instantiate all domains for the one you cut.
Right, it's combinatorial in your instantiations of the variables you cut, right? N minus C E squared, right? N minus C is our new N from our previous tree instantiation, E squared. Very, very fast for small c. Okay. So let's look at an example here. So let's choose a cut set. We'll instantiate the cut set in all possible ways, right? So we pick SA. That's definitely the one we want to cut out of this. It's the smallest one that gives us a tree, right? We assign it all of its possible values, and then we compute the CSP for each of those assignments, making sure that we have propagated via the constraints to its neighbors that choice, right? Because otherwise you're going to solve this, and NT is going to end up being blue here, and then you're not going to get a solution, right? Because at the end of the day, you have to concatenate the solution you determined from solving the tree problem with the solution that you fixed in advance, right? All of it has to be a solution. That's what you're trying to solve. Make sense? Okay, cool. Yep. Then you solve those. Then you're done. All right. So let's take 5 minutes break. Closer to half way through the class, and tell me the smallest cut set that results in a tree for this graph. When you're done, I know it's NPR, but this one gets some. Yeah. In general.
Yeah. I was just thinking that this problem.
No, so you could say, well, maybe not maybe not. But yeah, because each of these values is just some one of the values. Sorry, I never said my time. Let me just, okay, otherwise we'll be stopped.
Are we to assume that research always needs search based solely on heuristics, or is it just a different approach?
So the research I described in the class was always based on.
Okay. And so in general, we should assume that.
Yes.
Okay.
Sorry, shouldn't have.
Okay.
Y'all are my guinea pigs. Okay, let's get started again. Okay, smallest cut set results in a tree from the graph. Who says G? Who says H? Who says I? J, K, F, A, B, L, E, D, C, M. G and H. G and I. G and J. G. Okay, you see where I'm going with this? So the set of all possible cut sets is the power set, right? Everybody see why this might start to become a pretty hard problem. Anyway, what do you think from based on your superhuman or exactly human but super this algorithm intelligence? Yes. A and B. I think that's right too, and I'm not going to check. All right. So yes, if we cut out A and B, right, then we're left with the tree. Yes.
So could we optimize that, like the power set, prune it down to ordering the cut set by the number of edges associated with a node?
So you could imagine if this class was on graph theory and we were talking about solving this problem, a heuristic associated with cutting nodes that have lots of edges. But I'm not sure. Like that probably would work pretty well on practice. But there may be better heuristics-based solutions to minimum cut set. I'm not sure. But NPR. Okay. Moving on. Moving back. So if we had actually done this, and we had this cut set, how many times would we need to solve, let's say the domains are binary, how many times would we have to solve the tree problem? I mean, 4 times. Okay, good. All right, so that trade-off is starting to come into, right? Okay. All right, I'm going to talk about a concept here that is a little more complicated and won't be material that we test you on via homeworks, quizzes, or projects, but is worth noting, and that's that we can create a tree-structured graph from a more not tree-structured graph by a process called tree decomposition, which is where we start to change what it means to be a variable, and the variable becomes a sub-problem of the overall graph. And we can, if we're smart about how we choose those, result in a tree-like CSP where we've changed what it means to be an assignment and things like this. So we'll talk about this for a second. But the idea is that we're going to create a tree structured graph by using mega variables, where each mega variable encodes some part of the original CSP, and then we have to make sure that our sub-problems overlap in order to ensure that we're consistent with the original problem. Okay, so the idea is that we can take this sub-problem of this larger problem, and any valid solution to the larger problem is going to contain and encode a valid solution to the sub-problem, right? Okay, so this sub-problem is now one of our mega variables. This one will be the one adjacent to it, and we'll say decompose this original problem. That's meaning exclude it because we were smart about leaving connected components early. This is going to be our new problem, right? Okay, so this is mega variable 1. Mega variable 1 has a different domain, right? The domain of mega variable 1 is the set of valid assignments to that subproblem, right? The set of assignments to each of those old non-mega variables that satisfies the constraints associated with the mega variable subproblem. Make sense? Okay. So if we solve this subproblem, that's how we would determine this, right? We can also solve this one, and then this one, and that one too. We end up with a bunch of valid subproblems. But what's the issue here if we're not considering how these things talk to each other?
You're ignoring like the other edges out of like NT and NT.
Well, so all edges out of NT exist, and in at least one of the subproblems, right? The problem is that NT exists in multiple subproblems. So if I solve this problem and I make NT green, red, right? And then in this one, I made it green, that's a big problem, right? So we have to have constraints in between these things. Each of these has a different domain, and these constraints are going to be hard to describe potentially, but the idea is that we agree on a shared variable. Right? So now this is a tree of constraints in this formalization, right? We have some set of values in each of these mega variables domain. We could just solve this using our tree algorithm we had a little bit ago. But determining the domains, these can be expensive, making sure that you structure it right. You have to be more careful than I've described with how you structure this to make sure that your resulting solution is consistent, but I don't really get into it too much. But this is an option out there. If people look at this, it can be extremely powerful if you do it right. Okay. Cool. Let's talk about something called iterative improvement. We are now departing from the concept of traditional search. We did it. We talked about search. We're going to keep talking about search, but this is not search in the way we've described it so far. This is in fact going to be our first randomized algorithm. We're going to use it to solve these CSPs for now. Here's the idea. Iterative algorithms for CSPs. It's going to be kind of local search methods. So these are going to work with complete states. So you already have some assignment of the variables. It just might not be a valid assignment. Right? Okay, like this one. So say we're doing graph coloring again. We have these two adjacent nodes. They're not allowed to be equal to each other. I don't care yet. I have some full instantiation of the problem. Right? So then, to kind of formulate this for CSPs, we have an assignment with unsatisfied constraints, but it's complete. Right? We have operators that reassign values in our assignment. And that's it. There's no fringe. We're living life on the edge. Okay? All right, so we have some operator that may reassign this right value from red to blue. Now it satisfies its constraint. That's great. Yes?
Local search methods?
Local search compared to global search. So is this a concept that people have heard before? All right, so we're starting to wade further into the blurry line ocean between optimization and search. But the idea here is that your algorithm takes a local approach. It looks at what is immediately adjacent to me with some conceptual meaning of local, and I'm going to operate on that. And that's the only thing I know or care about. Compared with a global approach, an algorithm takes a global approach, which may result in something that's definitely going to work, some property, or is globally optimal, potentially if we're talking about optimization. Right?
So local in terms of possible states, kind of thing. Local to the states that they already are set at.
Yeah, so it's less formal than that, is how we're using it here. It just, there's some local information you're not considering global information. It's myopic in some conceptual way.
And it's not really like a sub-problem, it's just kind of what we can see directly around our problem.
It is a description for describing a property of an algorithm. That means it's kind of only looking near itself. Okay, so here's the algorithm. While not solved, that could come back to haunt us later, right? But that's what we're gonna do. While it's not solved, we're gonna randomly select any conflicted variable. Then we're gonna choose a new value for it that violates the fewest constraints, and we're gonna assign it to that. Then we're gonna do it again. Forever. Maybe. Right? Conceptually, this is like hill climbing, where your fitness function is the total number of violated constraints. It's not exactly that, but it's not. Pretty simple idea. So here's an example of how that might work with an n queens where n is 4 problem. Right? So to review, we have 4 queens, they sit in 4 columns, that's 4 to the 4, 256 possible states. In this example, we're going to move a queen in its column, that's going to be our operator. Right? So our variables are the columns, or the queens, depending on how you think about it, but it's functionally the same. The values they can take are their rows, right? And then what we're going to do is just move a queen in its column, right? Okay. So then our evaluation of the constraints are going to be the number of kind of attacks between this set of queens, right? Okay. So you can see we start with 5 total here. We pick one that violates the most. They all seem to violate the same number. That's cool. We pick one at random. Sorry, we pick one at random and we move it to a place that violates the fewest constraints. So I misspoke just now. Let's take a step back 10 seconds. We pick one at random and then we reassign it as a function of the remaining constraints. Make sense? So we pick the second one, for instance. We move it to the location that would have the fewest number of constraints. Right? That's the top row there. We have fewer constraints now. We take another one at random. That's going to be the third one. We move it to a place with the fewest number of constraints. We solve the problem. Yes.
You had mentioned selecting the one that has the most violations. Was that what you had mentioned?
That is what I misspoke and said.
Oh, okay.
Maybe that might be a smart way to start doing things, but for now you're just picking it random.
Okay.
All right, so let's look at how that works on our iterative improving. That's the algorithm on this big graph coloring problem we looked at last time. Yes?
Just to clarify with that last slide, when you said moving it to the position with the fewest number of constraints, that doesn't necessarily mean that it's 0 constraints. It could move it to another invalid position, but it's likely a better position.
Yeah. And it could, in fact, introduce new constraints you didn't have before. Right? There could be no assignment that has 0 constraints. There could be an assignment that has fewer constraints than you started with, but introduces new constraints. They're not old constraints, they're new constraints, etc. Right there. You just kind of try to lower the number of constraints as we go. Okay, let's see how this works on this. All right. Okay, so we switched to iterative improvement. We're assigned. Right? So we now have an instantiation for all of our variables. It's gross, it doesn't work. Right? But it's there. We just have violated constraints. Those are going to be highlighted here in yellow. Okay. So now we're going to start one by one, picking at random a node, reassigning its value. And let's see how it works. So there's a new constraint. That constraint didn't exist before, right? But we don't really care. keep going. Hey, it solved it. Solved it much more quickly than any, I think, of our previous algorithms did. In fact, this algorithm can solve n queens in functionally constant time for an arbitrarily large number of queens. With some high probability. It may not work, right? You may bounce around between things that are constrained for forever, but in practice, it works well.
Yeah, did you say it could get caught in a loop? Constraining and then unconstraining?
Yeah, so you can imagine with low probability picking some value, there is no way to lower the number of constraints. There's maybe 3 of these exist in the graph, you just bounce back and forth between them, right? Or there's some maybe pathological cases where you're always introducing some new constraint. Maybe the problem actually doesn't have a solution. We've never said these problems have solutions, right? The other algorithms that we've talked about will tell you that after d to the n, at least computations, right? Order d to the n computations, it'll come back and say, no, it didn't work.
This one, you don't know.
This one won't. No, this will just go forever.
Yeah.
Yes?
So with this algorithm, are you just looking one step ahead and trying to make things better in the very next step?
Yeah, so that's the local part of local.
Okay.
Yep, there's no global viewpoints here. You're not taking any higher order information. You're just saying, where am I now? How do I make it a little better? Go there, try again. Right? So what are some downsides to this? Actually, yes, question.
Oh, I actually had an upside.
What's your upside?
I like that it does move towards a solution, or at least partial solution. So if you're solving a problem where partial solutions help, right, for the moment, it's actually really powerful for getting towards partial solutions.
Yeah, potentially. This might improve some initialization for some other algorithm that's solving maybe something like this. Yeah, totally. What are some downsides to this? We've kind of talked about it. Is it complete? Will it find a solution if one exists for sure? Not necessarily. Is it optimal?
Not necessarily.
Yes.
Also the cost of checking for conflicts and checking if it's solved is possibly pretty expensive.
Yeah, depending on how you're doing it. Maybe. In practice though, for a huge number of problems, this works really, 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 really well. Like n queens. Okay. So this actually turns out to be true for any randomly generated CSP, except in a really narrow range of a very particular value, which is the ratio between the number of constraints and the number of variables. So if you look at this graph here, right, if you have a huge number of variables and not very many number of constraints, this is going to work with very high probability very, very well. That's tons of variables, tons of choices, almost no constraints, that's easy, right? It also works really, really well if you have a ton of constraints and very few variables. That's less intuitive for why that would be the case, but it is. That's because you're able to hone in on the right answer more quickly. But then there's this space right in the middle. There's some critical ratio here where, roughly speaking, your number of constraints and your number of variables are approximately the same. And it gets really hard. But it's hard in a way that you don't know easily how hard it is while you're doing it. Does anybody want to guess where on this graph the interesting problems that you run into all the time lie?
Critical ratio.
Turns out, unfortunately. I love this illustration. So we have the world of CSPs, right? And most of it's awesome. And then there's this one part that's no good, right? That's where the hard problems are.
Isn't that also why
There's where it is. Well, so that's an interesting question. Is the difficulty of solving a problem what makes it interesting?
Because once you solve it, it's not interesting because you have a solution, right?
Well, so there's a difference, I think, between solving a problem that is a general problem, which is what we do in computer science, right? And solving an instance of a problem, right? So solving the instance of a problem might be interesting because the result of solving that problem is something you value strongly. Like solving how to identify cancerous cells under a microscope slide automatically, right?
Yeah.
That's I would argue, interesting for reasons that aren't how hard it is. Right? But as computer scientists, we frequently say, the hard problems are the more interesting problems, they're the things worth working on, especially with getting research.
Because we can abstract away from the context and just look at the problem.
Well, computer science is the study of problem solving, right? It's not solving specific problems, it's solving an abstract set or an abstraction of a problem, right? So that you can then apply that solution to anything. And as computer scientists, we care strongly about how hard problems are to solve. That's why we lump them in all these groups, right? We talk ad nauseum about whether or not these groups are the same thing or not, right? So very interesting, but yes.
Is the peak at R equals 1?
I believe it is, but it might be off a little bit. I'll check. Other questions? Yes.
We're randomly picking a value from the constraints and then we're changing it.
From the variable set.
From the variable set. What would be wrong about picking the one with the most amount of constraints?
I don't think there's anything wrong with that. In fact, it's probably a pretty good heuristic, but I could imagine that creating some oscillating behavior in some pathological case that would be bad. So you probably still want some stochasticity in your algorithm, right? Say with probability sum, I'm going to choose that heuristic. With other probability 1 minus that or something, I'm going to choose at random. Right? These are the kind of tricks we play to get around these issues. Yes?
I can imagine this is extremely effective for problems that have a lot of different solutions. Like, then your chance of happening across or happening close to one of those solutions when you randomly distribute variables is fairly high.
Yeah, I think that's the case. But if you start needing to enumerate all the solutions or start talking about quality of solutions, you might have an issue. But yeah, totally. Okay. So I kind of want to talk more about local search here for a second while we have some minutes remaining. So in summary, for CSPs, this is the last we'll see of CSPs other than in your homework and quizzes. CSPs are a special kind of search problem where states are partial assignments, goal tests are defined by the constraints and a notion of full assignment, right? The basic solution we talked about is backtracking search. That's built on depth first search. We talked about these speedups associated with ordering, filtering, and exploiting substructure. In not classical search, iterative min conflicts is often very, very effective. Okay? Cool. Goodbye, CSPs. Let's talk about local search. Okay. So when we talk about tree search, this keeps some unexplored alternatives on the fringe, right? That's how we're ensuring completeness. Local search, you just improve till you can't improve anymore, and you call it a day. Okay, so our new successor function, if we're going to conceptualize this as search, is going to be local changes. Generally, this kind of search is much faster and more memory efficient. You can see why, because there's no fringe, right? Much faster, depends on the problem, but generally speaking it is. But it's incomplete and suboptimal. Right? Okay, so I hinted at this notion of hill climbing, right? And so this is a pretty simple idea. The idea is that you have so now we're talking about kind of optimization maybe, but you have some landscape, right? This is associated where it's your variables defining your location in X and Y, for instance, in a 3D world, and then your height is your functional value. You're trying to find the optimum, right? You have X and Y as your decision variables. You try to find the one that is it, right? So hill climbing here is we take some random spot and we just improve locally and improve locally and improve locally. We climb this hill, but we can't climb anymore, and that's it. Okay. So what's bad about this approach? Is it complete? No. Is it optimal? No. Okay, so to bring this back from optimization into kind of search, where we don't have some costs associated with our states, but rather we're just trying to find some set of goals, you can imagine that this landscape is dictated by your proximity to the goal or some other measure of almost fullness, right? Okay, so it's not complete necessarily in that formalization. It's not optimal if you're talking about optimization, right? What's good about it?
It can get you to a local maximum very quickly.
You can, depending. It's really easy to implement. practice, there's some tricks you can do. You can start with many different random initializations and have all of those climbing hills, kind of a swarming type thing. There's lots of ways to work around this. But generally a very simple but very, very powerful concept in general. So let's look at this a little more. So here's our state, right? Here's our objective function. So we get to choose where we are in X, and then where we are in Y at that X is defined by our objective function, right? This can be true in 2D where we have this 3D landscape, right? It can be true in 3D where you have some 4D landscape, 5D, 6D, whatever, right? It's abstractable. But you have some current state, you're gonna climb until you can't climb anymore, right? So there's some topology kind of considerations of this space that you have to be careful with. One is that if you start here, you're gonna end up here, right? As people have already pointed out, this is a local maximum, but it's not a global maximum. But you don't know that. All you can see is what's around you, and what's around you says you're as high as you can go, right? You also have these shoulder regions, maybe, right? You find yourself here. Where do I go from here? Can't say, right? I'll probably just stop, right? Etc. So, really briefly, if we started at X, where would we end up? That's right. If we started at Y, where would we end up? Right. If we started at Z, pretty simple idea, right? This points to this notion of multiple randomly initialized searches, right? That worked really well. All right, let's talk about a version of this that's a little more complicated, called simulated annealing. Yes?
I don't know, but it reminds me of a lot of stuff in like physics and chemistry where stuff is trying to get to lower energy states and just kind of takes whatever is available.
Yeah, so you can look at like I've looked at, for instance, a long time ago, protein folding, right? Where you have some energy landscape associated with the configurations of your base atoms in your molecule or whatever.
And so like it takes a certain amount of energy to fold in certain ways. So like
yeah, so if you don't have energy being injected, maybe there's no way to get around that, right? There's these local minima and local maxima. So, yeah. For instance. But yes, definitely. Continuing some physics-based analogy, this algorithm is called simulated annealing. Is anybody familiar with the process of annealing in like metallurgy? Cool. This is an algorithm that has that as its kind of guiding analogy, but isn't too related to that after a very simple relationship. Okay, so the idea here is that you're kind of doing this local hill climbing search, but you're going to allow it some probability to escape local minima by moving in random directions. And you're going to have some schedule that's defined by this temperature that's generally getting lower. That's going to say, how much am I allowing this thing to bounce around randomly? Right, so I'm going to pick some action. That's going to say, move in some direction. I'm going to look at the value there with some probability. Well, if it's better, I'm just going to go there. With some probability, if it's lower though, I'm going to go there. And that probability is dictated by the current temperature, which is getting small. Does that make sense? You can read about this. It's been around for a long time. But it allows you to get around local minima. In fact, this has an interesting property where if t decreases slowly enough, this guarantees you're going to converge to the global optimum. This is a canonical example of a gradient-free optimization method, because you don't have to look at gradients.
Well, isn't the delta E a gradient though?
Delta E is sort of like some sample gradient, but it's not like an analytical gradient. You don't need a function that has well-behaved gradients or that has analytically defined gradients to make this work.
So it's not like an instantaneous gradient versus a more dispersed.
Exactly. Yeah. So it's, I mean, you're kind of saying, you're not even saying, oh, this is the gradient, I'm going to move in that direction, right? You're saying, it's better over there, I'm going to go there. Or it's worse over there, I'm going to go there anyway. I have used this in my work to optimize the design of robots specifically for patients. So you have some robot that you can fabricate right before you perform surgery on this person. You can make that robot's design specific to the patient itself, or their specific pathology. You can use this optimization to do that. Yes.
Now this isn't actually guaranteed to find the global maximum, is that right? Because it's kind of just randomly choosing new states.
It is Yeah, you should look at the proof. Hand wavy, it kind of boils down to this notion that in infinite time, you will sample arbitrarily close to the global maximum an infinite number. Yeah, so, interesting point, real quick before we go. In theory, this finds you the global optimum, but it's going to take infinite time, and in general, it may not converge very fast. Right? So if you care about finite time, which is what most of us care about, there may be better choices. All right, so let's stop there, and we'll continue.